The night sky is a familiar canvas of stars, planets, and distant galaxies. But if you could see the universe in X-ray vision, that tranquil scene would vanish, replaced by a raging, high-energy storm. This invisible light show is the cosmic X-ray background, a faint, all-pervading glow that is one of astronomy's deepest enigmas. By the end of this journey, you will understand 25 profound mysteries locked within this cosmic static, puzzles that have challenged our finest minds for over half a century. We are about to explore the hidden sources that could rewrite cosmic history, from supermassive black holes shrouded in dust to the possible decay of dark matter itself. What does this persistent whisper from the cosmos make you wonder about our place in the universe? The very first mystery begins with a simple, startling fact. In 1962, a team led by the physicist Riccardo Giacconi launched a rocket equipped with a Geiger counter, an instrument designed to detect high-energy radiation. They were hoping to study X-rays from the moon. What they found instead was a complete surprise, a faint, uniform fog of X-ray light coming from every direction in the cosmos. This was the cosmic X-ray background, and its discovery shattered a fundamental assumption. Scientists had long believed the vast spaces between galaxies were mostly empty and quiet, a true void. This faint, all-pervading glow proved that space was not empty at all. It was filled with something, a mysterious source of immense energy that was completely invisible to our eyes. This X-ray fog is fundamentally different from the more famous cosmic microwave background, which is the cooled remnant of the Big Bang's initial heat. The X-ray background is not a leftover from the universe's birth. It is a signpost of its violent, ongoing life. It is the combined light of countless high-energy events happening across space and time. The core of the mystery lies in its diffuse nature. If you look at a single star, you can point to it. But this glow is like trying to identify every single raindrop in a dense, pervasive mist that blankets the entire sky. Pinpointing the exact sources responsible for this uniform fog became one of astronomy's greatest quests. How could something so energetic be so perfectly spread out? And what was creating this cosmic static that filled the heavens? This discovery immediately created a second, more frustrating mystery. If this glow was the combined light of countless individual sources, why could we not see them? Our most powerful early X-ray telescopes pointed at the haze and saw almost nothing. It was like staring into a thick fog, knowing it was made of tiny water droplets, yet being unable to pick out a single one. This was the puzzle of the missing point sources. Astronomers were facing a version of Olbers' paradox, but for X-rays. The classic Olbers' paradox asks why the night sky is dark if the universe is infinite and filled with an infinite number of stars. For the X-ray sky, the question was flipped. If the universe is filled with discrete, powerful X-ray sources, why does it appear as a perfectly smooth, uniform glow instead of a sky littered with distinct points of light? The answer lay in a combination of distance and technological limits. The first X-ray telescopes were simply not sensitive enough. Think of them as having poor eyesight, able to see the bright glow of a nearby city, but completely unable to pick out the individual streetlights that created it from miles away. The true sources of the background were incredibly faint and incredibly far, their light stretched and diluted by the vast expanse of the cosmos. This launched a decades-long race to build a better instrument, a telescope with the resolution and sensitivity to finally dissect the fog. The scientific community knew that buried within that uniform static was a cosmic census of the universe's most violent phenomena. Unlocking it required a technological leap, a new eye on the sky capable of seeing the unseen. What would it find when it finally peered deep into the glow? That better eye on the sky finally arrived with a new generation of X-ray observatories. These powerful telescopes peered deep into the faint glow and began to pick it apart. resolving the uniform fog into millions of distinct points of light. The identity of these sources revealed a cosmic powerhouse, supermassive black holes feasting at the hearts of distant galaxies. These are not the quiet, dormant black holes of our own Milky Way, but active galactic nuclei, or AGN, engines of unimaginable violence. When a supermassive black hole actively pulls in surrounding gas and dust, that material does not fall in quietly. It spirals into an incredibly hot, glowing disk, so energetic that it blasts out X-rays, sometimes outshining all the stars in its entire galaxy combined. This is the leading theory for the cosmic X-ray background, a universe filled with the roaring energy of these cosmic beasts. But not all AGN are the same. Some, known as quasars, are so phenomenally bright they can be seen from the edge of the observable universe, their light traveling for billions of years to reach us. Others, called Seyfert galaxies, are closer and quieter, but still host a brilliantly active core. Yet there is a crucial twist that makes them perfect candidates for the background glow. Many of these AGN are hidden. Thick clouds of cosmic dust and gas can shroud the central black hole, blocking its visible light completely. But high-energy X-rays are like bullets. They can punch through that obscuring material, though they are weakened in the process. From our perspective, these hidden monsters appear as faint, smeared sources of X-rays, their true ferocity masked by distance and dust. This explains why the background appears so smooth. We are not seeing the brilliant, unobscured quasars, which are relatively rare. Instead, we are seeing the faint, muffled glow of countless obscured AGN, each one a hidden inferno scattered across the cosmos. Their sheer numbers and their muted, distant light blend together into the pervasive static we observe. Yet this elegant solution presents its own profound challenge. When astronomers add up the light from all the AGN they have now detected, from the brilliant quasars to the faint, shrouded ones, the numbers do not quite add up. There seems to be a shortfall, a portion of the cosmic X-ray background that remains unexplained. It appears that active black holes alone cannot account for all the X-ray fog. So what other cosmic phenomena are contributing to this universal whisper? What else is lurking in the darkness, adding its voice to the chorus? This obscuration creates a serious accounting problem for astronomers. While our telescopes can see the brilliant, unobscured quasars and the moderately hidden black holes, there is an entire population of the most heavily cloaked monsters that are nearly invisible. Their thick shrouds act like a cosmic filter, absorbing the very type of X-rays, the lower energy ones, that most telescopes are designed to detect most easily. It is as if you were trying to count people in a dense fog by listening for their voices, but a large group is speaking in whispers too soft for you to hear. You know they must be there, but your current methods cannot register them. This is the missing population, the hidden AGN that could make up the shortfall in the X-ray budget. To find them, we needed a new strategy, a way to listen for a different kind of signal. We needed telescopes that could detect higher energy, harder X-rays. These energetic photons are like armor-piercing rounds. They have the power to punch straight through the thick clouds of gas and dust that block their softer cousins. This is where missions like NUSTR, the Nuclear Spectroscopic Telescope Array, enter the story. NUSTR is a specialist, designed to see the high-energy X-ray universe with unprecedented clarity. It is not looking for the shouts of the quasars. It is listening for the faint, high-pitched whispers of the most deeply buried black holes. By surveying the sky in this untapped energy range, NUSTR and observatories like Chandra are finally pulling back the curtain. They are finding these elusive objects by the thousands, revealing a universe that is far more crowded with hidden, feeding black holes than we ever suspected. Each new detection adds another piece to the puzzle, helping astronomers finally quantify the true contribution of these obscured giants to the pervasive cosmic static. Yet even as we find more of them, a deeper question emerges. Why are so many of the universe's most powerful engines hidden from view? What does this preference for obscuration tell us about how galaxies and their central black holes evolved together over billions of years? Quasars represent the ultimate expression of a black hole's power. These are the active galactic nuclei turned up to 11, so ferociously bright that their light can outshine a trillion suns. At the heart of a quasar, a supermassive black hole, often weighing billions of times the mass of our Sun, is pulling in matter at a staggering rate. This material, swirling in a frenzied accretion disk, heats to millions of degrees and blasts out a torrent of radiation across the entire electromagnetic spectrum, with X-rays being one of its most dominant voices. In the early universe, these cosmic beacons were far more common, a testament to a more violent, gas-rich era when black holes feasted with abandon. So, it seems logical to assume that these brilliant monsters are the primary architects of the cosmic X-ray background. If we could add up the X-ray light from every quasar that has ever shone across all of cosmic history, surely that would account for the diffuse glow we see. Yet this is where the mystery deepens. When astronomers perform this cosmic accounting, they run into a fascinating problem. The combined brilliance of all the quasars we have catalogued, while immense, does not perfectly match the intensity and the specific energy signature of the X-ray background. There appears to be a spectral mismatch, a subtle difference in the light's fingerprint. It is as if you were listening to a grand orchestra and could clearly hear the trumpets and the violins, but the overall sound of the symphony has a deeper, richer bass note that those instruments alone cannot produce. This discrepancy suggests that while quasars contribute a massive portion of the background, they cannot be the whole story. Their brilliant, unobscured light is the wrong color, so to speak, to explain the entire X-ray fog. This points us back toward the population of hidden, obscured black holes, the ones that emit a different kind of X-ray light, and perhaps to other, even more exotic sources waiting to be discovered. The universe is showing us that its most luminous beacons, for all their power, are only one part of a much larger and much quieter chorus. But the spotlight on brilliant quasars and hidden monsters may have blinded us to a much quieter, more numerous population. Beyond the drama of active galactic nuclei, the universe is filled with ordinary galaxies, much like our own Milky Way. These are not the blazing powerhouses of the early cosmos, but stable, mature islands of stars. The question is, could the faint, combined light from billions of such normal galaxies also be a significant contributor to the cosmic X-ray fog? The answer lies within the galaxies themselves, in their own local sources of high-energy drama. A normal galaxy is not truly peaceful in X-ray light. It glows with the accumulated light of countless binary star systems where one star has died, leaving behind a super-dense corpse, a neutron star or a stellar mass black hole. If this dead star orbits a living companion, it can violently siphon gas from its neighbor. As that gas spirals down onto the neutron star or black hole, it heats to phenomenal temperatures, producing intense, localized beams of X-rays. These X-ray binaries are scattered throughout a galaxy like our own, along with the lingering, expanding shells of supernova remnants, where shockwaves heat gas to millions of degrees. Even the diffuse, superheated gas that floats between the stars in vast coronae emits a faint X-ray whisper. Alone, a single galaxy like the Milky Way is a quiet murmur in the X-ray sky. But the universe contains an almost uncountable number of such galaxies. When you add together the faint X-ray glow from every normal galaxy across the vast expanse of space, could this collective murmur rise to become a noticeable part of the background static? This is the faint galaxy dilemma. To solve it, astronomers point our most powerful telescopes at seemingly empty patches of sky for days or even weeks at a time. These deep field observations are like core samples drilled into the cosmos, revealing layer upon layer of faint, distant galaxies. By meticulously counting these galaxies and measuring their individual X-ray brightness, scientists can perform a cosmic sum. They add up the light from every detected galaxy to see if it fills the budget gap. The results are both clarifying and puzzling. These countless faint galaxies do contribute, but their combined light appears to be just a fraction of the total background. It seems the universe's X-ray voice is not dominated by the quiet hum of normal galaxies, nor is it solely the roar of active black holes. It is a complex chorus where no single type of source can claim the entire stage. So if even the combined might of every type of galaxy we know falls short, what other, more exotic performers are waiting in the wings, adding their unseen energy to this universal signal? Perhaps the answer does not lie within the galaxies at all, but in the vast, empty spaces between them. This brings us to a hypothesis that redefines our notion of emptiness, the idea of a hot intergalactic medium. For decades, astronomers have theorized that the cosmic web, the large-scale structure of the universe, is not just made of dark matter. The filaments of this web, the great bridges connecting clusters of galaxies, are predicted to be filled with an incredibly diffuse, yet unimaginably hot, gas. This is the warm, hot intergalactic medium, or WHIM. The gas in these filaments is so thin, with perhaps only a few atoms per cubic meter, that it constitutes a better vacuum than any we can create on Earth. Yet, it is heated to temperatures of millions of degrees by the gravitational pull of the cosmic web itself. And gas at that temperature, no matter how thin, glows in X-rays. So, could this pervasive, superheated fog be the missing source of the cosmic X-ray background? The theory is profoundly elegant. It suggests that the faint X-ray glow we see is not just the sum of distant points of light, but the very signature of the universe's skeletal structure, the hot breath of the cosmic web itself. Proving this, however, has been one of observational astronomy's most difficult challenges. The WHIM is so diffuse that its X-ray signal is incredibly weak, a whisper lost in the static of brighter, more localized sources. It is like trying to hear the hum of the entire ocean by listening from a mile above, while surrounded by the roaring engines of speedboats and cruise ships. Astronomers have tried to detect it by looking for its subtle absorption fingerprints in the light of distant quasars, or by stacking countless observations to amplify its faint signal. While there have been tantalizing hints, a definitive, direct detection of the WHIM's full contribution to the X-ray background remains elusive. This leaves a crucial question unresolved. How much of the cosmic static is the roar of hidden black holes? And how much is the faint, universal sigh of the hot gas that weaves the galaxies together? This challenge of detection is a battle against extreme faintness. To find the warm, hot intergalactic medium, astronomers turn to a technique perfected in other branches of science, the search for absorption lines. Imagine a brilliant quasar, a beacon of intense X-ray light shining from the distant universe. As its light travels for billions of years to reach us, it passes through the invisible filaments of the cosmic web. The superheated, thin gas of the WHIM can steal a tiny fraction of this light, but only at very specific energies corresponding to the elements within it, primarily highly ionized oxygen. The result should be a unique fingerprint, a series of tiny, dark dips in the quasar's otherwise smooth X-ray spectrum. Finding these dips would be the smoking gun, proving the WHIM exists and measuring its properties. Yet, this search has been plagued by frustration. The expected absorption lines are incredibly weak, often buried in the statistical noise of the detectors themselves. It is like trying to detect a single, specific note being faintly hummed in a massive, roaring concert hall. The signal is simply too subtle for most telescopes to pick out with certainty. The other approach is to try and see the WHIM directly by its own faint emission. This is perhaps even more difficult. telescopes must stare for immense periods at the supposedly empty spaces between galaxy clusters, hoping to catch a uniform, diffuse X-ray glow that is slightly brighter than the already pervasive cosmic X-ray background. The problem is that this emission is so faint and so spread out that it blends perfectly into the very static we are trying to explain. We are essentially trying to see a faint, uniform mist by looking through a brighter, overlapping fog. This has led to a technological arms race, pushing the limits of our instruments. Missions like XMM Newton and Chandra have provided tantalizing hints, possible detections of the WHIM in a few specific filaments. But a comprehensive map, a full confirmation that this hot gas truly forms the universe's skeleton, remains just beyond our grasp. The failure to definitively find it is as telling as a successful detection would be. It forces us to ask whether our models of the cosmic web are correct, or if the gas is even hotter or more diffuse than we ever predicted. What if the universe is hiding half of its normal matter not in galaxies, but in this ghostly, seething web that forever eludes our sight? Even our most powerful eyes on the X-ray universe, like the Chandra Observatory, cannot dissolve the entire cosmic fog. A stubborn fraction of the background glow, perhaps 10 to 20% of it, remains stubbornly unresolved. After decades of observation and technological triumph, a fundamental piece of the cosmic puzzle is still missing. This lingering static is the final frontier of this mystery. What could possibly be so faint, so diffuse, or so exotic that it eludes detection by our finest instruments? One compelling possibility is a population of sources that are simply too distant and too faint for even Chandra to see. We are pushing up against the limits of our technology, trying to hear a whisper from the very edge of the observable universe. These could be the first, most primordial black holes, feasting in galaxies so young that their light has been stretched and weakened by the expansion of the universe for nearly its entire history. Their collective murmur, stretched thin across time and space, could be that final, missing piece of the static. But there is a more thrilling alternative. This unresolved fraction might be a sign of something entirely new, a phenomenon that does not fit into our current catalogs of cosmic objects. Could it be the collective decay of sterile neutrinos, a hypothetical form of dark matter, or the faint echo of cosmic strings, theoretical defects in the fabric of spacetime itself? The existence of this unresolved glow is a humbling reminder that our maps of the cosmos are still incomplete. It is a blank space on our chart, marked only by the words, "Here there be dragons." What kind of creatures are we missing, silently contributing their energy to the universal whisper that has captivated us for over half a century? To understand that unresolved static, we must journey back to the very beginning, to an era before the first stars and galaxies fully formed. This is the cosmic dawn, a time of profound darkness pierced by the ignition of the universe's very first suns. These primordial stars were not like the ones we see today. They were monsters, behemoths containing hundreds of times the mass of our own sun. They lived fast and died violent deaths, collapsing into the universe's first black holes after only a few million years. It is the furious activity of these first black holes and their descendants that could be the key to the lingering X-ray fog. Imagine a universe filled not with the mature galaxies of today, but with countless small, young galaxies, each hosting a newly formed black hole greedily feeding on the pristine gas around it. Each one would be a tiny, brilliant source of X-rays. Individually, they are now far too distant and faint for our telescopes to pick out. But their collective, smeared-out light, stretched by the expansion of the universe over billions of years, could be the very signal that remains unresolved in the cosmic X-ray background. It is the faint, fossilized echo of creation's first monsters. How did these first black holes form so quickly? One leading theory points to a process called direct collapse. In this scenario, vast clouds of primordial gas did not fragment into many stars. but instead collapsed under their own immense gravity directly into a single, massive black hole, bypassing the star stage entirely. These black holes would have been born with a head start, weighing thousands of solar masses from their very first moment. They would have immediately begun feasting, generating torrents of X-ray radiation that helped heat and reshape the young cosmos. Finding evidence for this ancient population is now a primary goal for the James Webb Space Telescope. While Webb sees in infrared light, not X-rays, it can hunt for the host galaxies of these first black holes. It can look for the unique chemical signatures or the intense infrared glow from hot dust that would betray the presence of a hidden, supermassive black hole in a galaxy, so young its existence should be nearly impossible. If Webb can find these primordial giants, it will provide the crucial missing link, connecting the faint, uniform X-ray static we see today to the violent birth pangs of the very first structures in our universe. What would it mean if the background radiation is partly the ghostly afterimage of creation itself? So we have a census of cosmic contributors, from brilliant quasars to hidden monsters, yet their combined light still does not perfectly match the universal static. This leads us to a spectral fingerprint that does not fit, a puzzle known as the hardness problem. Think of the cosmic X-ray background as having a specific color, but in the world of X-rays, color means energy. The background glow is surprisingly hard, which is a technical term meaning it is rich in high-energy X-rays. Now, when astronomers add up the light from every single point source they have identified, from the blazing quasars to the faintest obscured black holes, the resulting color is softer. It contains fewer of those powerful, high-energy photons than the background itself. This is a fundamental mismatch, like mixing every paint color on your palette and finding the resulting shade is lighter than the one on your wall. Something is missing from our mixture, a component that adds a specific, energetic red tint. The prime suspect is a specific class of the most heavily cloaked black holes, known as Compton thick active galactic nuclei. In these systems, the shroud of gas and dust is so incredibly dense that it acts like a lead shield. When lower-energy X-rays try to escape, they are almost completely absorbed, scattered, or lost. But the highest-energy X-rays are like armor-piercing rounds. They have a much better chance of punching straight through the obscuring material and traveling across the universe to reach our telescopes. Therefore, a population of Compton thick GN would emit a light that is skewed, biased toward those higher energies. If we are missing a large number of these specific objects from our cosmic census, then our sum of known sources would naturally appear too soft, explaining why the background remains so hard. Yet confirming this is exceptionally difficult, because by their very nature, these are the most difficult objects in the universe to find. Their faint, hard whisper is easily lost in the cosmic noise. This hardness problem forces us to wonder if we have truly accounted for all the hidden monsters, or if the universe is hinting at an even more exotic source of high-energy radiation, one that we have not yet even begun to imagine. The very glow of the cosmic X-ray background is a kind of time machine. This faint static is not a single snapshot of the universe. It is a layered fossil record, a cumulative archive of every high-energy event that has occurred over the past 13 billion years. The light from a nearby, hidden black hole might have traveled for a few 100 million years to reach us, while the X-rays from a quasar at the edge of the observable universe have been on a journey for almost the entire age of the cosmos. All these signals from different epochs and different distances arrive at our telescopes simultaneously, blended together into that single, pervasive glow. Decoding this timeline is the ultimate challenge, a cosmic detective story where the crime scene is the entire history of the universe. The central clue is the intensity and the hardness of the background itself. Why does it have this specific brightness, this particular energy signature? The answer is written in the rise and fall of the populations that created it. We know the early universe was a more violent place, a golden age for quasars and active black holes. Vast reservoirs of gas fueled these monsters, allowing them to shine with incredible brilliance. The cosmic X-ray background should therefore hold the echo of that ancient frenzy. A significant portion of its light should come from that early, energetic era. Yet, the background we measure is not as intensely hard or as bright as some simple models of that violent past would predict. This is the paradox. It tells us that the story is not just about brilliant quasars in the early universe, but about a balancing act across time. The muted glow we see today suggests a cosmic changing of the guard. As the universe aged and gas supplies were depleted, the brilliant, unobscured quasars became rarer. But the hidden, shrouded black holes, the ones that emit a different kind of light, may have become more common, or their collective activity may have peaked at a later cosmic time. The faint static we measure is the sum total of this entire evolutionary saga. It forces us to ask whether the peak of black hole feeding occurred at the dawn of time, or much later in an era of hidden, matured giants. Unraveling this timeline is like trying to reconstruct the entire history of life on Earth from a single, blended sound recording of every creature that has ever lived. How do we separate the roar of the ancient dinosaurs from the buzz of the modern insects? For astronomers, the key is to look deeper. By observing the X-ray sky at different sensitivities, they can peel back the layers of time. The faintest sources detected in a deep field image are typically the most distant, giving us a glimpse of the young universe. By counting these sources and measuring their brightness at different distances, we can begin to build a movie from a single, frozen frame, charting the evolution of cosmic violence. The cosmic X-ray background is the final, integrated product of that movie. Its specific character is the direct result of how many black holes were feasting, and how brightly they were shining at every single chapter in cosmic history. So, the next time you look up at a dark, quiet night, remember that the true story of the cosmos is written in an invisible, high-energy light, a fossilized echo of a past that was anything but tranquil. Our cosmic detective story now leads us to the largest structures ever assembled by gravity, the colossal galaxy clusters. Each one is a metropolis of 1,000 galaxies or more, all bound together by the invisible hand of dark matter. But the true marvel of a cluster is not the galaxies themselves, it is the space between them. These vast intergalactic spaces are not empty. They are filled with a superheated plasma, a gas so incredibly hot it glows not in visible light, but in a brilliant fog of X-rays. This gas is heated to millions of degrees by the sheer gravitational crush of the cluster's immense mass. The combined light from the hot gas in every cluster across the universe creates a diffuse, pervasive X-ray glow. So how much of the cosmic X-ray background is simply the accumulated breath of these cosmic giants? The puzzle is one of accounting on a universal scale. We can easily see and measure the brightest, most massive clusters nearby. But what about the countless fainter, more distant ones? There could be an entire population of low-mass clusters that are simply too dim for our telescopes to pick out individually. They would be like distant, smoldering embers compared to the roaring bonfires of the great clusters we can easily see. Yet, in their vast numbers, their faint, collective glow could be a significant and largely invisible portion of the background static. This is the cluster contribution conundrum. To solve it, astronomers perform a cosmic sum, adding up the X-ray light from every known cluster in the sky. The result is always the same. Even when we account for the clusters we cannot see directly, their total emission seems to be just a small fraction of the total background. The mighty clusters, for all their immense size and seething heat, are not the primary architects of the X-ray fog. They are a crucial part of the chorus, but their voice is a deep, resonant bass note in a symphony dominated by the higher-pitched shrieks of active black holes. This realization forces a profound shift in perspective. It tells us that the energy of the universe is not concentrated solely in its greatest cities. The true power, the source of the pervasive whisper, is far more democratically distributed, hidden within the hearts of billions upon billions of individual galaxies. So if these colossal structures are mere contributors, not the main event, what does that tell us about where the universe truly concentrates its most violent energy? Buried within the X-ray fog are structures so vast and faint they were almost invisible to us, the ghost halos. These are enormous, tenuous clouds of X-ray light that stretch hundreds of thousands of light-years beyond the visible edges of galaxies and clusters, like a phantom atmosphere on a cosmic scale. Their discovery was a surprise, a subtle glow that only the most sensitive observations could tease out from the background static. To explain their origin, we must look to one of the universe's most fundamental lights, the cosmic microwave background. This cooled remnant of the Big Bang fills all of space, a sea of low-energy photons. The theory suggests that within these ghost halos, electrons are racing at nearly the speed of light. When these relativistic electrons collide with the ancient microwave photons, they transfer a tremendous amount of energy, like a professional pitcher hitting a baseball. This process, called inverse Compton scattering, knocks the meek microwave photon into the high-energy X-ray regime, creating the faint, diffuse glow we detect. This means a ghost halo is not a cloud of hot gas in the traditional sense, but a cloud of incredibly energetic particles, a cosmic particle accelerator on a truly monstrous scale. But where do these electrons get such immense speed? They are likely flung out by the central supermassive black hole in a galaxy, its jets pumping energy into the surrounding space for eons, or accelerated by the colossal shock waves from merging galaxy clusters. The existence of these halos forces a profound question. Are these ghostly structures a common yet overlooked feature of the cosmic landscape? If they are widespread, then every galaxy and cluster could be surrounded by an immense, invisible corona of high-energy particles. Their combined, faint light could be woven throughout the cosmic X-ray background, a subtle tapestry we are only just beginning to see. How many more of these phantoms are we still missing? And what does their silent presence tell us about the energetic winds that shape the evolution of the entire cosmos? The universe's most elusive substance might be hiding in plain sight, woven into the very static we have been trying to decode. This brings us to the most speculative and thrilling frontier of all, the possible connection between the cosmic X-ray background and dark matter. We know dark matter exists because of its gravitational pull on galaxies, but we have never directly seen it. It is the universe's ghost, making up most of the matter but refusing to interact with light. What if, under certain conditions, this ghost reveals itself not with a shout, but with an X-ray whisper? Theoretical physicists propose that some types of dark matter particles could decay or annihilate each other, transforming their mysterious mass into pure energy and releasing photons, including X-rays. One leading candidate is the sterile neutrino, a hypothetical heavier cousin to the standard neutrinos we know. If these sterile neutrinos exist, they could be unstable, slowly decaying over billions of years and producing an X-ray photon at a very specific, predictable energy. Another candidate, WIMP, or weakly interacting massive particles, could annihilate when they collide with each other, creating a burst of radiation that would include X-rays. The combined faint glow from all such events across the cosmos could be subtly contributing to the background static, a hidden thread of dark energy woven into the brighter tapestry of black holes and hot gas. The hunt for this signature became electrified by a specific discovery, or rather, a tantalizing hint. Several independent teams analyzing data from galaxy clusters and the Milky Way's center reported a faint, unexplained emission line at an energy of 3.5 kilo-electron volts, often called the 3.5 keV line. This was not a broad smear of light, but a sharp, spectral spike, exactly the kind of fingerprint you would expect from a specific particle like a decaying sterile neutrino. It was as if, after decades of listening to the chaotic roar of the cosmic orchestra, we heard a single, pure, and unfamiliar note that no known instrument could produce. The excitement was palpable. Had we finally found the first direct signal of dark matter? The answer, frustratingly, remains maybe. Other observations failed to confirm the line, and alternative explanations, such as complex atomic processes from potassium atoms in hot plasma, were proposed. The 3.5 keV line sits in a notoriously difficult part of the spectrum to observe, where instrumental effects can sometimes mimic a real signal. So the hunt intensifies. The next generation of X-ray telescopes, like the European Space Agency's planned THENA mission, are being designed with the sensitivity to definitively confirm or rule out this line. Finding a dark matter signal in the cosmic X-ray background would be a monumental breakthrough. It would mean that this pervasive static is not just a fossil of cosmic violence, but also a live broadcast from the invisible 85% of the universe's matter. What if the answer to one of physics' greatest mysteries has been bathing us in its faint, high-energy light all along? That single, pure note at 3.5 kilo-electron-volts sent a shockwave through the world of astrophysics. This was not the broad smear of light from hot gas or the roar of a black hole, but a sharp, spectral spike. A fingerprint so specific it seemed to point directly to a new kind of particle. The initial observations came from stacked data of galaxy clusters and from the heart of our own Milky Way, places where dark matter is thought to pile up in its greatest densities. The signal was faint, but it was exactly where and what many theorists had predicted for a decaying sterile neutrino, a leading dark matter candidate. For a moment, it seemed the ghost had finally spoken. Yet, the cosmos rarely gives up its secrets so easily. The initial excitement soon collided with the rigorous, often frustrating, process of scientific confirmation. Other teams, using different telescopes and fresh observations, pointed their instruments at the same targets. Some saw nothing but smooth, unbroken static where the line should have been. The 3.5 keV signal was so faint, it lived right at the edge of what our current technology could detect. In a realm where subtle instrumental effects can sometimes create phantom lines, mirages in the data. The debate intensified, splitting the community. On one side, proponents argued that the line was real and consistent across multiple independent analyses. They pointed out that a mundane astrophysical source would likely produce a more complex signal, not this clean, singular spike. Could it be, they asked, that we are finally seeing the slow, steady decay of the universe's most abundant yet invisible substance? On the other side, skeptics offered alternative explanations. They proposed that the line could be the result of something far more ordinary, just poorly understood. What if it was emitted by a complex cascade of atomic processes involving sulfur or potassium ions swirling in multimillion-degree plasma? Our models of these turbulent, hot gases are not perfect, and it is entirely possible that a rare transition in a common element could mimic the dark matter signature we so desperately seek. This is the core of the 3.5 keV mystery. It is a classic scientific standoff, a cosmic whodunit where the prime suspect is either a ghost or a familiar actor in an unfamiliar disguise. The resolution demands more than just better data. It requires a fundamental leap in our understanding of both the exotic and the ordinary. The next generation of X-ray observatories, like the Advanced Telescope for High-Energy Astrophysics, a THENA, is being designed with this very mystery in mind. Its unprecedented sensitivity and spectral resolution will act as a supreme cosmic court, hearing the evidence with such clarity that it should deliver a final verdict. It will either confirm the line as the first true glimpse of dark matter, forever changing our place in the universe, or it will erase it from the map, forcing us to confront the unsettling possibility that the ghost is even more elusive than we dreamed. What if the answer has been hovering just beyond our reach, a faint note in a universal song we are only now learning to hear? beyond the grand dramas of galaxy clusters and supermassive black holes, a quieter, more numerous population contributes to the cosmic static. The universe is filled with the dead. When stars like our Sun exhaust their fuel, they fade into dense white dwarfs. More massive stars die in supernova explosions, leaving behind even denser neutron stars or stellar mass black holes. These stellar corpses are not always silent. In binary star systems, a dead star can orbit a living companion. If they are close enough, the immense gravity of the corpse can violently steal gas from its neighbor. This stolen gas does not fall gently. It spirals inward at nearly the speed of light, forming a searingly hot accretion disk around the white dwarf, neutron star, or black hole. The temperature in this disk soars to millions of degrees, causing it to shine with incredible intensity in X-rays. A single one of these X-ray binaries can outshine the Sun by 100,000 times, but only in this high-energy light. Every galaxy, including our own Milky Way, is populated by thousands of these faint, flickering beacons. Alone, each one is a tiny point of light, but across the entire observable universe, their numbers are staggering. Could the combined glow from countless trillions of stellar corpses, each feeding in a binary dance, form a significant part of the cosmic X-ray background? The mystery lies in the sheer scale of the accounting. How many of these systems exist in a typical galaxy? How brightly do they burn on average, and for how long? Astronomers must create a cosmic census, extrapolating from the populations we see nearby to estimate the total contribution from every galaxy we cannot see individually. The faintest and most distant of these binaries would be completely invisible to our telescopes, their individual light lost in the noise. Yet, in their unimaginable numbers, their collective murmur could blend into a pervasive sea of faint points, a fundamental component of the universal static. This leads to a profound question about the nature of the cosmos. Is the X-ray sky not just dominated by the occasional roar of a supermassive black hole, but also by the endless, soft hiss of countless stellar graves, each one a testament to a star that lived and died? Scattered throughout other galaxies, far beyond the familiar stars of our own Milky Way, there are pinpricks of light that defy all logic. These are the ultraluminous X-ray sources, or ULXS, and they shine with a ferocity that should be impossible. A typical stellar mass black hole, the remnant of a dead star, has a strict limit to its brightness, a law of physics called the Eddington limit. This is the point where the outward pressure from its own radiation becomes so strong that it pushes incoming material away, effectively turning off the black hole's own food supply. Yet ULXS blast out hundreds, even thousands of times more X-ray light than this fundamental limit should allow. They are not quite as bright as the supermassive black holes at galactic centers, but they are far brighter than any normal stellar process. So what are these cosmic lawbreakers, and how are they generating such staggering power? The leading theory points to a missing link in the black hole family, the intermediate mass black hole. We know of small black holes born from dying stars, and we know of supermassive ones, millions of times heavier, that lurk in galactic cores. But the existence of black holes in between, weighing a few hundred to a few 100,000 solar masses, has been notoriously difficult to confirm. An intermediate mass black hole would have a higher Eddington limit simply because of its greater gravity, allowing it to accrete matter and shine more brightly without breaking the rules. Finding a population of these would solve the ULXS mystery neatly. Yet there is another, even more fascinating possibility. What if these are just normal, stellar mass black holes after all, but they are feeding in a way we thought was impossible? This is the theory of super-Eddington accretion. Imagine a black hole not sipping politely from a stream of gas, but gorging itself in a chaotic, messy feast. So much material is falling in at once that it cannot all spiral in an orderly disk. Instead, it forms a thick, puffy envelope, a kind of cosmic traffic jam where photons of light struggle to escape. This trapped radiation creates an immense outward pressure. But if the inward pull of gravity from the infalling gas is even stronger, the black hole can temporarily violate its theoretical limit, shining with a brief, spectacular intensity. This would make a ULX not a new type of monster, but a familiar one in an extreme and gluttonous state. The true puzzle for the cosmic X-ray background is one of numbers. How many of these ultraluminous sources are out there? They are not common in any single galaxy, but when you consider the trillions of galaxies in the observable universe, their total population could be immense. Each one is a brilliant, if short-lived, candle in the cosmic dark. If they are numerous enough, their combined light could be a significant, and previously overlooked, thread in the tapestry of the X-ray fog. We thought we had categorized the main players, but these exotic objects remind us that the universe still holds surprises. Could a multitude of these brilliant, lawless beacons, scattered across all of space and time, be the source of the lingering static that our telescopes cannot resolve? For all its apparent uniformity, the cosmic X-ray background is not perfectly smooth. This leads us to a subtle but profound search, the hunt for large-scale anisotropies. The word anisotropy simply means direction-dependent, a fancy term for a faint pattern, a ripple in the cosmic static. The core assumption has always been that the glow is the same in every direction, a universal hum with no discernible features. But what if that is not entirely true? What if, on the very largest scales, there are imprints, subtle variations in the intensity of the X-ray fog that trace the underlying skeleton of the cosmos? Finding these ripples would be like discovering faint writing on a blank page, a hidden message about the distribution of all matter, both seen and unseen. The primary target of this search is the imprint of the first, most massive structures to form after the Big Bang. Theorists predict that the earliest supermassive black holes did not wake up uniformly across the infant universe. They flickered on in great clusters, in vast cosmic webs of their own, creating bubbles of intense X-ray radiation that expanded and overlapped. The subtle shadow of those first great assemblies, their collective signal slightly stronger in one part of the sky than another, could still be frozen into the background we see today. It would be the fossilized echo of the universe's first cities. Detecting this signal is a monumental technical challenge. The variations are expected to be incredibly faint, a fluctuation of just 1 part in 1,000 or even less, buried deep within the data. It is like trying to measure the microscopic texture on the surface of a perfectly still pond. Our instruments must be exquisitely sensitive, and our methods for subtracting the foreground noise from our own galaxy and from known point sources must be nearly perfect. The hunt is on, with teams scouring the all-sky maps from observatories like XMM Newton and Swift, using complex statistical tools to tease out any hint of a pattern. A confirmed detection would be a direct window into the adolescent universe, revealing not just the locations of the first monsters, but the gravitational tides of dark matter that guided their formation. The silent, uniform fog we perceive may, in fact, hold the faintest of whispers, telling the story of how everything we see first began to clump together. The very concept of a background is one of constancy, a stable stage upon which the universe's dramas play out. But what if that stage itself is subtly shifting? This leads us to the profound mystery of time variability. Is the cosmic X-ray background truly a fixed, eternal glow, or does it, over cosmic timescales, actually flicker? To our instruments, which have only been observing for a few decades, the glow appears perfectly steady. But our human timescale is a single, frozen snapshot in a movie that has been playing for over 13 billion years. Imagine if you could speed up that movie, watching eons pass in seconds. You would not see a static fog, but a shimmering, dynamic tapestry. The light would pulse and surge in different parts of the sky, as vast populations of active galactic nuclei, the primary engines of the background, wake up, feast, and then fall silent. A giant cluster of quasars igniting in one cosmic epoch would create a temporary bright patch in the X-ray sky, a glow that would persist for millions of years before slowly fading as those black holes exhaust their fuel. The background we measure today is the sum of all these overlapping, out-of-sync flickers, averaged into the uniform hum we perceive. Measuring this flicker directly is a mind-bending challenge. It would require observing the same patch of sky for not decades, but for millions of years, a task far beyond any mission we can conceive. Yet, there might be an indirect way to detect this cosmic pulse. By mapping the precise distances to millions of individual X-ray sources, we can reconstruct a history of black hole activity. We can see that quasars were more common in the past, meaning the background was almost certainly brighter and harder 8 or 10 billion years ago than it is today. The glow we see is not a monument, but a living fossil, still cooling from a more violent youth. Detecting even a hint of modern-day variability would be a revolution. It would mean that the grand cycle of feeding and famine for supermassive black holes is an ongoing process, that the universe's energy budget is not fixed but breathes with a rhythm too slow for us to feel. What does it mean for our understanding of the cosmos if its most fundamental light is not a constant, but a heartbeat? At the most extreme end of the spectrum, the cosmic X-ray fog does not simply fade away. It sharpens into a high-energy tail, a realm where X-rays blur into the domain of gamma rays, the most energetic form of light in the universe. This is the frontier of the truly violent, a place where photons carry a punch powerful enough to shred atoms. The sources of these incredible photons must be nature's most powerful particle accelerators. The prime suspects are blazars, a special and terrifying class of active galactic nucleus. Imagine a supermassive black hole, but instead of emitting energy in all directions, it focuses its wrath into two colossal, narrow jets of radiation and subatomic particles shooting out at nearly the speed of light. A blazar is simply an active galaxy where one of these deadly jets is pointed like a cosmic blowtorch directly at Earth. From our privileged, and perhaps frightening, vantage point, the jet's intense emission is amplified enormously, making blazars the brightest and most variable objects in the gamma-ray sky. Their contribution to the highest energy end of the background is immense, a screaming siren in the cosmic static. But are they the only performers on this stage? The sheer power required suggests even more exotic origins. Could some of these photons be the final flash from the annihilation of dark matter particles, a process that would convert their entire mass into pure energy in a burst of gamma rays? Or are we seeing the faint, blended light of hypernova, the ultra-powerful supernova explosions that birth magnetars and gamma-ray bursts, events so bright they can be seen clear across the observable universe? The high-energy tail is a shadowland of cosmic extremes, hinting at phenomena so rare and catastrophic that we have not yet been lucky enough or patient enough to witness one up close. What other unimaginable events are encoded in this faint, energetic whisper at the edge of our perception? This faint X-ray fog might be the very map we need to find half the universe. I do not mean dark matter, but the missing ordinary matter, the atoms that make up every star, planet, and our own bodies. According to our most precise cosmic accounting, only about half of the normal matter predicted to exist by our models of the Big Bang has ever been found. This is the mystery of the missing baryons, and its solution is almost certainly tied to the warm, hot intergalactic medium, the seething gas of the cosmic web. The leading theory is that these lost atoms are not in galaxies at all, but are spread throughout the vast filaments, heated to millions of degrees by the gravitational pull of the dark matter scaffolding. A gas that hot, even if incredibly thin, shines in X-rays. This means the cosmic X-ray background is not just a problem to be solved. It is the most promising tool we have. If we can learn to read its subtle variations, to separate the faint, uniform sigh of this hot intergalactic gas from the roar of black holes, we could finally weigh it. We could take a cosmic census of this elusive matter and close the budget on the ordinary stuff of the universe. It is a breathtaking possibility that by deciphering one profound enigma, we might solve another. The faint static that has puzzled us for decades could be the very signal that leads us to the missing atoms of creation. What if the answer was hiding in the background all along? Even the most powerful telescope does not look out at a pristine cosmos. Its view is clouded by a local haze, a foreground of X-ray static generated right here in our own cosmic neighborhood. This is the instrumental foreground, a practical but profound mystery that challenges astronomers to separate the true cosmic whisper from a cacophony of local noise. Picture our Milky Way not just as a collection of stars, but as a vast atmosphere of incredibly thin, million-degree gas, a hot halo that envelops the entire galaxy. This halo itself glows faintly in X-rays, creating a diffuse screen that lies between us and the distant cosmic background. Then there is the interference from our own solar system. The solar wind, a constant stream of particles from the Sun, slams into Earth's magnetosphere, and this collision can generate a soft X-ray glow that changes in intensity with solar activity. Even the spacecraft itself contributes. Energetic particles from deep space, cosmic rays, can strike the telescope's detectors directly, creating tiny flashes of light that mimic the arrival of a genuine X-ray photon from a distant quasar. Untangling this mess is a monumental task of cosmic forensics. Astronomers must create intricate models of all these local phenomena, carefully subtracting their predicted signals from the total data collected. It is like trying to hear a faint, distant symphony while standing next to a roaring waterfall, and you must first digitally remove the sound of the water before you can even hope to hear the music. The success of this cleaning process is everything. A tiny misstep, an oversubtraction or an undersubtraction, could leave behind a false signal or erase a real one, potentially leading us to imagine cosmic phenomena that do not exist, or to miss the subtle signature of dark matter itself. How can we ever be certain that the whisper we finally isolate is truly from the edge of the universe, and not just the echo of our own celestial backyard? The quest to decode the cosmic static is accelerating toward a technological crescendo. The next generation of X-ray observatories, now on the drawing board, promise to be so powerful they will transform the faint fog into a sky ablaze with individual points of light. Leading this charge is the European Space Agency's THENA, the Advanced Telescope for High-Energy Astrophysics, a mission designed to be 100 times more sensitive than our current best telescopes. Imagine if your entire life you had only seen the world in a blurry haze, and then someone handed you a pair of glasses of unimaginable clarity. That is the leap a THENA represents. It will peer so deep into the cosmos that it will resolve nearly all of the lingering, unresolved fraction of the cosmic X-ray background into its discrete sources. We will finally see the raindrops that make up the mist. This will solve fundamental puzzles. It will provide a definitive census of the most heavily obscured black holes, the Compton-thick population, directly testing the hardness problem. It will weigh the warm, hot intergalactic medium with precision, likely solving the missing baryon mystery by mapping the hot gas in the cosmic web. And with its exquisite spectral resolution, it will deliver a final verdict on the 3.5 kilo electron-volt line, determining once and for all if we are seeing the decay of dark matter or a complex atomic process. Yet, the true legacy of a THENA and its successors will not be the answers they provide, but the new questions they will inevitably raise. When we can see every single source, what new patterns will emerge? Will we discover entirely new classes of X-ray objects that we cannot yet conceive of? The history of astronomy teaches us that every time we build a better window on the universe, we are humbled by the sheer strangeness we find. The end of one mystery is simply the beginning of the next, deeper layer of cosmic enigma. This final mystery is perhaps the most ambitious of all. We have journeyed through 24 cosmic puzzles, from hidden black holes to ghostly dark matter. But the ultimate goal is to weave every single thread into one coherent tapestry. The dream is a unified theory of the cosmic X-ray background, a single mathematical recipe that accounts for every last photon in that faint, high-energy fog. We already know the main ingredients: the roaring energy of active galactic nuclei, both the brilliant quasars and the shrouded monsters, provides the base of the sauce. The faint, collective murmur from countless normal galaxies and their stellar corpses adds a subtle depth. The superheated breath of galaxy clusters contributes a rich bass note, while the seething warmth of the cosmic web, the WHIM, might be the pervasive broth that holds it all together. And then there are the exotic spices, the potential whispers from decaying dark matter and the brilliant, law-breaking flares from ultraluminous sources. We have all the ingredients laid out on the cosmic counter. The grand challenge, the final mystery, is knowing the exact proportions. How much of each component do we need to mix to perfectly recreate the universal static we observe? A little too much quasar light, and the model becomes too soft. Not enough obscured black holes, and the hardness problem remains. Too much hot gas from the cosmic web, and the model's large-scale structure would look wrong. Getting the recipe perfect is one of the grandest outstanding problems in modern astrophysics. It is the ultimate act of cosmic cooking, and we are still tasting the soup, adjusting the seasoning, trying to balance a flavor that has been simmering for 13 billion years. What will it mean for our understanding of the universe when we can finally write down that single, elegant equation? A formula that encapsulates the entire violent, dynamic, and hidden history of the cosmos in one faint, all-pervading glow. From the ghostly breath of the cosmic web to the faint decay of dark matter, these 25 mysteries reveal a universe teeming with hidden energy. The cosmic X-ray background is far more than a static screen of light. It is a living archive, a grand narrative written in high-energy photons. Each point of unresolved static, each spectral mismatch, and every unexplained flicker is a chapter in the story of cosmic evolution, from the violent birth of the first supermassive black holes to the slow, steady sigh of the missing baryons. Solving these puzzles is not about filling in a single blank on a chart. It is about rewriting our fundamental understanding of how the universe works, how its structures assemble, and where its true power resides. The journey to decode this universal whisper is just beginning, and the next generation of telescopes promises revelations we can scarcely imagine. We want to know which of these 25 mysteries captured your imagination the most. Was it the hidden population of black holes, the search for dark matter's signal, or the ghostly halos surrounding galaxies? Let us know your thoughts in the comments below, and subscribe to join us as we continue to explore the deepest enigmas of space.